All right, we're going to continue with proportions in Chapter 2, but we're going to be looking at this particular part of proportional situations. We're going to be looking at variation and what that means. So we're going to review what direct variation, the properties of direct variation equation. We're going to learn how to read a direct variation graph and use that. We're also going to learn how to read a direct variation equation to find missing values in a data set. And we'll go through some examples to see what that means. Okay, let's erase some of my writing here. So as I reveal each one of these scenarios, start looking for a pattern here. If you increase your study time, your grades should what? Increase or decrease? If you're studying more, you're going to increase your grades, right? Here too, if you increase your hours at work, you should be paid more. So your paycheck will also increase. If you decrease your running speed, so if you're running slower, the distance you're going to cover is going to be less, right? So the distance you run is also going to decrease. As you decrease the time you spend practicing, your skills at that sport are also going to decrease. So what's the pattern here? I see increased study time, increased grades, increased hours at work, increased paycheck, decreased speed, decreased distance, decreased time practicing, decrease your skill. So hopefully you saw that pattern. As I increased one thing, so in two of these situations, I increased one variable, the other variable also increased. And for the other two situations, as I decreased one variable, the other variable also decreased. Okay, that's a direct variation relationship. As one thing increases, the other also increases. As one decreases, the other also decreases. So as Charlie Brown says, did you ever notice the number of people watching is directly proportional to the stupidity of your actions? As your actions become more embarrassing, it seems like more people are watching. All right, so this is what we call a direct variation equation. So this shows that the quantities x and y, depending on what those are and what situation are we talking about, running speed and running distance, those are the variables we might be talking about. They're directly proportional to each other if this is true. If y equals k times x, and I'm going to explain what k is. We'll go through some examples of what k is in a moment. But we call k our constant of variation. Okay, so in other words, if I want to make a batch of cookies, and a batch of cookies takes 4 cups of flour. If I want to make 2 batches of cookies, then I'm going to use 8 cups of flour. So in that case, in my cookie making, my constant of variation is 4, or 4 cups, because every time I want to make another batch, I need to add another 4 cups of flour, right? So I'm going to multiply how many batches I need to make by 4. So this would be considered a constant of variation. Here's another form of that. So take a look. If I divide both sides by x, what happens to x? I've eliminated it there, and I just have another version of my direct variation equation. So this is just, again, like I said, another version of it. Y divided by x equals k. Okay, so notice in that version, direct variation is related to division. My constant of variation comes from the division of my 2 variables. Again, we'll take a look at more of those examples. Direct variation is proportional. This is sort of another way of saying proportional. So just like we've been setting up proportions in the past, we have y is both on the top, x is both on the bottom, right? That's kind of what we've been talking about with setting up proportions. Again, direct variation is just like division, y over x. Let's take a look at what these look like on a graph. The graph of a direct variation relationship, like my making of cookies, that's a direct variation relationship. If I graph that, it's always going to pass through the origin of the graph. It's always going to pass through 0, 0. And that's always going to be true for every direct variation relationship. If I graph a situation and it looks like this, that is not direct variation. It does not pass through the origin of the graph. Every single one will pass through the origin of the graph, right? So if you look to the left, down here, when my constant of variation is greater than 0, I'm going this way, I'm going up towards the right. When my constant of variation is less than 0, I'm going up towards the left. Right, so I went ahead and wrote in what my constant of variation is for each of these graphs. And on the left, my constant of variation, K, is 1. Now look at the bottom. It says the steepness of the line depends on what? In my graph on the left, if I go and I increase my constant of variation, if I say now K equals 2, what's going to happen to that line is it's going to become steeper. So my constant, or the steepness of my line depends on the value of K. Now, on the other hand, in this graph over here, let's say I use a fraction that's less than 1 as my constant of variation. So let's say K equals 1/2. Well, what happens then to my graph is it becomes less steep. So the graph on the left, as I increase my constant of variation in the positives, my line becomes steeper. As I decrease that into the fractions, that becomes less steep. Now it's going to be the same thing over here. I just have negatives instead. So the K equals -1. And just like in my other one, if I do K equals -2, that line is going to become steeper. And if I say K equals -1/2, my line becomes less steep. So the steepness of the line depends on that constant of variation. It depends on your K value. So a couple of examples. You're paid $7.40 per hour at your job. That's direct variation. Each bottle of juice costs 99 cents. So it's really pretty simple if you look at it this way. So every hour I'm paid $7.40. That means my constant of variation is $7.40. Every single bottle of juice costs 99 cents. As I buy more bottles of juice, I'm spending more money, increase and increase. And again, that 99 cents is what's determining how much you're spending. That's your constant of variation. As you work another hour, you add another $7.40. As you buy another bottle of juice, you add another 99 cents. So remember that equation, y equals kx. So if I wanted to use that equation for this scenario here, the one on the bottom, again, if 99 cents is my constant of variation, I'm going to say y equals 99 cents times x. Okay, so if I buy 7 bottles of juice, y equals 99 cents times 7. That's a direct variation relationship. So you can see it's pretty simple in those situations. All right, now we have to look at calculators, though. So take out your calculator and follow along. All right, so go ahead and go into y equals in your calculator and enter in this equation, y equals 2.1x. Now this is direct variation because it's in that form, y equals kx, and my constant of variation is 2.1. So let's go ahead and enter that in. So y equals, and let's move this up a little bit, y equals 2.1. And remember, x is up here. Let's look at the red buttons. Y equals 2.1x. Okay, so from there, what we're going to do is set a standard window and then find our table of values. Okay, so when I go to set a standard window, I'm just going to hit window. And I want, actually, you know what, let's do this. This will be easier. Hit zoom. And when you go into zoom, you'll see that number 6 says standard. So right away, that will set me at my standard window. Notice this goes through the origin of your graph, right? Looks like I have a line over there on the right. Looks like I didn't erase or get rid of something in my y equals, so we'll go back and do that. But notice that diagonal line, it goes through the origin. Every direct variation equation has to go through, a direct variation situation has to go through the origin. I'm going to go back into y equals again and see where that line is coming from. Oh, you know what? I think it's coming from my x equals. Let's pause for a moment. All right, now that I got rid of that line, that x equals line, we can just see our direct variation equation here. So again, it goes through the origin as every direct variation situation should. All right, so I'm good to go. I want to use my table though. So to use my table, again, look at the keys I'm pressing by looking at what's in red. So I'm going to go second and graph, and that's going to get me my table of values. Okay, so from this table, what I want to do is find the cost of 15 items. So on my table of values, I'm going to look at where x is 15. So I'm going to scroll down. I'm going to get to x is 15. And I'm going to see that my y value is 31.5, or in this case, $31.50. So that's the cost of 15 items using my table. So next though, so that was, what did we say, $31.50. How many items for $12.60? Well, when I used my graphing calculator a minute ago, I saw that my y values were my prices, right? So this over here, oops, I'm not going to write on there. This over here on the right was price. So if I want to look for how many items is $12.60, I want to now scroll down, or scroll up in this case, to find a price of $12.60. Oh, and I just passed it. So it looks like right here, my y is $12.60, which means I have purchased 6 items. You can see that that 6 is highlighted. So how many items for $12.60? 6 items. So that's how I can use my table of values to find different to find my x or my y in a direct variation relationship. But let's look at these. How am I going to solve each one of these equations? So I have 21 equals 2.7x. So this is a little bit of review, but it's related. I want to divide by 2.7, right? I'm canceling out that 2.7. In other words, those are dividing out to 1, and I'm left with x alone. So pause for a second, do 21 divided by 2.7, and see what you. So if you do that division correctly, you should get x equals 7.8. So in this case, 2.7 is my constant of variation, y equals kx. K is 2.7, and I get an x value of 7.8. All right, how would I solve this one? So for this one, I have some multiplication to do. So I'm going to do 81 times 0.31, or 31 hundredths. And then I sub equals 4x. I'm going to pause again and see if you can come up with that solution. So for this one, I would have multiplied my 81 times 0.31 to get 25 and 11 hundredths. And then my second step would have been to divide by 4 in order to get x alone. And I end up with 6.2775 equals x. All right, what about this one? X over 5 equals 0.32. In other words, x divided by 5 equals 0.32. If I want to undo divided by 5, then I'm going to multiply both sides by 5. Right, that's going to undo that division. So I have x alone, and I'm going to do 0.32 times 5. And we're going to get x equals 1.6. Finally, in this one, now this is a little bit different, so pay close attention to this one. So remember, I have y equals kx. You got to memorize that direct variation relationship, right? But another version of that is y divided by x equals k. In other words, I can get my constant of variation by dividing y by x. That's this type of situation. So this is a y divided by x equals k. Okay, so still proportional, still direct variation, but it just looks a little bit different. So how would I find x in this case? Well, x is in my denominator. In other words, it's divided by x. If I want to undo divided by x, I'm going to multiply each side by x, right? That eliminates my x, and now I have 17 equals 0.5 times x, or 0.5x. Now you can finish that by saying, all right, divide both sides by 0.5 to undo that divided by 0.5. And now I just need to do 17 divided by 1/2. I want to take a moment and do a little mental math here. So 17, come over here, 17 divided by 1/2 is really just the same as saying 17 times 2. So 17 times 2 is 34. So some of these we don't really need a calculator for. So x in this case is 34. These are all direct variation relationships, and sometimes we have to find different variables depending on the values that we have. In this last case right here, I had my k, right? I also had my y value, but I needed to find my x value, and those are some of the things that we're going to be practicing.